Hey, it's Art from my new microphone. In this video, let's discuss the different types of compression and how they can be used in your mixes. Compression, short for dynamic range compression, is a dynamics processor that acts to reduce or compress the dynamic range of a signal, hence the name. It does so by effectively reading the loudest parts of a signal and attenuating those while leaving the quieter parts of the signal uncompressed. A compressor will act to reduce the gain of an input signal relative to a sidechain signal that is feeding a gain reduction circuit. Typically, this sidechain signal is taken from the input signal. However, we can also have an external sidechain as well. This is the case in the typical sidechain compression technique that we use in mixing and music production. This is, of course, a very simple breakdown of how compression actually works, but the main key concept to take into account here is that we have an input signal going into the compressor, then a sidechain signal either taken externally or internally within the compressor that will affect a gain reduction circuit that will act to reduce the amplitude of that input signal. The compressor only acts to attenuate the signal if and when the sidechain signal goes above a set threshold. The amount of compression or gain reduction that happens to the signal is dependent on the ratio of the compressor, which is typically in an x/1 value. That states that for every x dB above the set threshold, the compressor will only output 1 dB above the set threshold. Other compression parameters worth quickly discussing here are the attack and release times. The attack time refers to the rate of change and how quickly the compressor will react to a signal as it surpasses the set threshold. Conversely, the release time tells us how quickly the compressor will fully disengage once that signal drops back down below the set threshold. Hard knee compressors have a very strict threshold where anything above the threshold will be compressed by the set ratio and everything below will be uncompressed, whereas soft knee compressors have a much more gradual shift from non-compression to compression characteristics. With those quick parameters out of the way, let's now jump into the variety of compressor topologies that we will encounter as we go through mixing, how they work, and how we can use them in our mixes. We will go through each of these compressor topologies in alphabetical order rather than in order of popularity. In this video, we will be covering digital compressors, diode bridge compressors, FET or field effect transistor compressors, optical compressors, PWM compressors or pulse width modulation compressors, variable mu or tube compressors, and of course VCA or voltage controlled amplifier compressors. Starting off with digital compressors, a digital compressor is a digital signal processor that effectively applies the effect of compression on digital audio signals. With DSP or digital signal processing, these compressors can be designed or programmed with a variety of different compression and harmonic saturation characteristics. Different aspects of different analog compression types, which we will get to shortly, can be combined in these digital compressors to create something new and unique, and transparency can be achieved in these digital compressors that far exceeds the limitations of analog circuitry. There are many digital compressors that are designed to be very transparent, while there are many others that are designed to emulate their analog counterparts, particularly when it comes to audio plugins. In this way, digital compressors are a sort of mixed bag when it comes to characteristics, so it's hard to pin down specific characteristics about these types of compressors. It's pretty much the case that whatever characteristics we are after in a compressor, we are likely to find them in one digital compressor or another. Alright, moving on now to diode bridge compressors, which are a little bit rare compared to the others we will be discussing. These diode bridge compressors utilize a pair of diodes in a balanced bridge configuration, hence the name, to apply variable attenuation to the input signal. Typical characteristics of diode bridge compressors include very fast attack and release times, nonlinear compression that adds sonic character via harmonic distortion. They require very low-level input signals to not be overloaded, and because of that often require a lot of output gain, which often worsens the signal-to-noise ratio and introduces more noise than we may want in the audio signal. Diode bridge compressors operate with a bridge configuration of diodes. Typically, 2 pairs of diodes are set up in a diamond array. The audio signal is applied across 2 corners, while the control signal is applied against the opposite 2 corners. A diode generally only allows electricity to flow in one direction. However, there is typically a small region where the conductance of that diode will vary proportionally to the voltage applied across it. These small regions allow these diodes to act effectively as voltage-controlled attenuators in cases such as the diode compressor. For all of this to work, a diode bridge compressor must have the following: matched diodes to reduce an otherwise very high level of distortion in the signal, a balanced signal throughout the compressor because of the pairs of diodes, and an input signal that already has a rather small dynamic range in order to again fit within that small region of the diode's transfer curve where the conductance varies proportionately with the voltage applied across it. There's a lot that goes into these diode bridge compressor designs, as it's very difficult to make them sound great, and this is likely why they are not overly popular on the market today. Transformers are used to balance the signal and also to drop the level going into the compressor, as well as bring it up on the way out of the compressor. These transformers can add distortion to the signal along with the actual gain reduction circuit itself, and it's important to really nail the design of these compressors so that this distortion is actually sonically pleasing to the ear rather than very detrimental to the signal. When designed correctly, diode bridge compressors can sound very punchy and add a nice harmonic saturation to the signal passing through. The diode bridge compressor design has been made relatively popular by Rupert Neve Designs and Neve. Two popular diode bridge compressor designs include the Neve 33609 and the Rupert Neve Designs 535. Moving on, we have our FET compressors. A FET compressor is a compressor type that utilizes a field effect transistor at the core of its gain reduction circuit. These compressors are known to be very fast acting while still being able to preserve the transient information of the signals that they compress. Characteristics of FET compressors typically include very fast attack and release times, nonlinear compression that adds character via harmonic saturation, additional saturation due to the inclusion of transformers, and that they tend to require low-level input signals, which means that they require more output gain at the output, which can worsen signal-to-noise ratio in the output signal. FET compressors are typically designed in a feedback topology where the sidechain signal that acts upon the gain reduction circuit is actually taken after the gain reduction stage within the compressor. This sidechain signal is then fed into the field effect transistor that effectively acts as a voltage-controlled resistor in its linear range and gives us a very linear style of compression. To work within this linear range, the FET compressor often has to drop the signal level and then to boost it back up at the output stage, often with a transformer, which can add a little bit of distortion and harmonic saturation to the signal. Because of this inherent distortion characteristic that many FET compressors have, they're often cherished for their aggressive character. They're often used on vocals, drums, and guitars, and other instruments that really need to pop out and be a little bit more aggressive within the mix. As I mentioned earlier, FET compressors are very fast acting and can deliver significant gain reduction when set up correctly. However, they are also great for preserving transient information, especially as we increase that attack time variable. The most popular FET compressors on the market are the URI or Universal Audio 1176, originally released in 1967, and all of the revisions since then. All right, moving on next, we have our optical compressors. An optical compressor is an analog compressor that utilizes a light element and an optical cell to control the dynamics of a signal in its gain reduction circuit. As the amplitude of the input audio signal increases, the light element emits more light, which causes the optical cell to attenuate the output signal that much more. A few general characteristics of optical compressors include that they have low distortion thanks to their light-dependent resistors, or LDRs. They have relatively slow attack and release times, even though light is the fastest thing on Earth. They have nonlinear attack and release times that are largely dependent on the frequency of the sound passing through, and they generally sound fairly transparent, especially when compared to other compressor types. As I mentioned, optical or opto compressors utilize a light source and a light-dependent resistor or optical cell to achieve their compression. When there is no light shining on the light-dependent resistor, its resistance is very high, and as we increase the brightness of the light, that resistance drops off into very low levels. The input signal of an optocompressor effectively feeds its lamp, and so as the input amplitude increases, so too does the amount of light within the gain reduction circuit. As the amount of light increases, the LDR's resistance drops very low and more attenuation happens to the signal. Although light itself is incredibly fast, optical compressors are often rather slow because the LDR within these optical compressor gain reduction circuits are very slow. These light-dependent resistors are also not overly linear when it comes to attack and release times. Compared to many other compressor types, optical compressors are relatively simple in design and sound rather transparent because of the low distortion characteristics within their gain reduction and audio circuits. That said, harmonic coloration can be added to these units with the use of transformers and other circuitry within the compressor design itself. Because of their relative transparency and their slow reaction times, optical compressors are often not used on tracks that have a lot of transient information like drums or vocals. However, they can excel on many other tracks to help smooth them out without coloring them too much to help them fit into the mix. The most popular opto compressors are based on the Teletronics LA2A design that was originally released in 1965. Next up, we have PWM or pulse width modulation compression. PWM compressors utilize pulse width modulation to effectively alter the amplitude of the input signal, thereby compressing it. The design of PWM compressors is often much more complex than that of the other compressor types. However, by adjusting the parameters available to us, we can adjust the PWM system and thereby adjust the compression being applied to the audio signal running through the PWM compressor. The typical characteristics of a PWM compressor include a high level of transparency, very fast attack and release times if we want them, and a very flexible set of parameters to really hone in and adjust the compression being applied to the audio signals passing through them. Pulse width modulation can be used to reduce the average amplitude or level of an audio signal by effectively chopping that audio signal up into discrete parts known as pulses. And as the name would suggest, pulse width modulation then modulates the width of these pulses over time. Each pulse effectively turns the audio signal on and off. Now, this is done at such an incredibly fast rate that we don't hear it as a choppiness in the signal, but rather as a signal level reduction. The average level of the signal that has been affected by pulse width modulation is then sent to the compressor's output. The width of each pulse is largely defined by the PWM duty cycle, which may be represented by an on-time percentage parameter on the compressor. The longer the pulse width modulation is on relative to off, the more signal level will pass through. Remember that it's the average signal level that is passed through the PMW, and that the pulse width modulation happens incredibly fast to avoid unwanted distortion and side effects. The design of PWM compressors is deeply complex, and I won't even pretend like I know the inner workings of these compressors. However, with the typical parameters of attack time, release time, ratio, threshold, we can use these for ourselves as mixing engineers and audio engineers to our full advantage. When designed correctly and optimally, PWM compressors have the potential to be the fastest acting and most transparent compressors available on the market today. Although rarely used in mixing, PWM compressors have the potential to sound great on pretty much everything thanks to their great flexibility and transparency. The most popular PWM compressor is the Pi compressor. If you're finding this video informative thus far, I would invite you to hit that like button and to also subscribe for more content here on the My New Microphone YouTube channel. I'm just getting started and I'd love to have you aboard. Thanks. All right, our penultimate compression type is the variable mu compressor. A variable mu or variable gain compressor is an analog compressor that has its gain reduction circuit centered around a vacuum tube or a valve. As the input signal increases past a certain point, the current being sent to the grid of the tube can no longer follow it linearly, effectively causing a reduction in the overall output of the tube and the compressor itself. In other words, by driving the tube into nonlinearity, we can cause compression to the signal. Typical characteristics of a variable mu compressor include slight harmonic distortion of the signal, relatively slow attack and release times, and a soft knee that has a very program-dependent ratio. In other words, a variable mu compressor does not have a hard threshold where it will start applying compression at the threshold and above. Rather, a variable mu compressor will begin compressing well below the threshold at a lower ratio, and it will only reach its full ratio at some point well beyond the threshold. As mentioned, a variable mu compressor will have a tube at the heart of its gain reduction circuit. Typically in audio, we think of tubes as amplifiers, but they can also act as attenuators, especially in the case of variable mu compression. These compressors are considered program dependent, where again, the ratio will actually increase as the input signal increases in the variable mu compressor. This means that they are inherently soft knee compressors, and many variable mu compressors don't even have a parameter to control the ratio. The nature of vacuum tubes also gives variable mu compressors relatively slow attack and release times as the tube reacts slowly to the changing amplitude of the input signal. This results in smooth dynamic range compression, which is often enhanced sonically by the slight harmonic saturation provided by the tube. Because of these traits, variable mu compressors are often cherished as bus compressors or even as mastering tools. I should mention here that many other compressors from different compressor types utilize tubes in their design. However, these tubes are typically used at the makeup gain stage or the output gain stage. In variable mu compressors, the tube is actually at the heart of the gain reduction circuit. Famous variable mu compressors include the Fairchild 660 and 670, along with the Manley variable mu. And finally, we have VCA compressors or voltage-controlled amplifier compressors. A VCA compressor, as the name would suggest, is an analog compressor that utilizes a voltage-controlled amplifier at the heart of its gain reduction circuit. The input signal is split via an integrated circuit into a detection path, which will ultimately act upon the VCA, and an output path. The detector path is effectively manipulated by the typical parameters we will find on a VCA compressor, like attack time, release time, knee control, threshold, ratio, etc., and effectively acts as the voltage-controlled amplifier of the output circuit. However, instead of amplifying the signal, it acts to attenuate it. Typical characteristics of a VCA compressor include a high level of transparency and very low distortion, along with very flexible control over the different parameters mentioned earlier. Because of the inherent transparency and flexibility of VCA compressors, they are often chosen for a wide variety of roles when it comes to compression inside a mix. From heavy transient drum tracks to pads and soft strings to mastering, VCA compressors can be found pretty much anywhere inside a mix. A downside for VCA compressors is that sometimes the control voltage, which is responsible for the gain reduction or compression of the circuit, may actually leak into the audio signal path. This can lead to artifacts and distortion, especially if we're hitting the compressor particularly hard, but in the rare cases that it does leak, it tends not to be a severe issue. I just wanted to bring that up as a potential downside, as I've spent the last few minutes praising the VCA compressor topology. There are so many great VCA compressors on the market today, but a couple that I wanted to share with you here in this video are the API 2500 and the SSL G series bus compressors. Alright, so that sums up the different types of compressors. I have more in-depth articles on each of these compressor types on my blog at mynewmicrophone.com. I will leave links to all of those in the description box down below. I will also leave a link to the My New Microphone mixing cheat sheet. Of course, there are no cheat codes when it comes to mixing, as every mix is different and requires different mix processing. But this cheat sheet I put together acts as a sort of reference guide to help you make the right mixing decisions at the right times in your mixes. So it's free. There's a link to that in the description box down below as well. If you like the content here, I would invite you to subscribe to the channel, and I'll also put up a few other videos here having to do with mixing and compression in particular for you to check out. So click on one of these videos, check out the resources in the description box down below, and I will see you in the next video.